Graphene. Why hasn't the material of the future arrived yet? Hey engineering lovers, have you ever heard of graphene? The incredible one-atom thick material with properties that seem straight out of science fiction? It's stronger than steel, more conductive than copper, and almost transparent. This material was promised to be a revolution in electronics, energy, medicine, and materials. But look around you. Your smartphone isn't made of graphene. Cars don't have a graphene body. And the question that many of you might be asking and that we're going to answer today is, if graphene is so miraculous, why don't we see it around? The answer isn't in science, but in engineering. Let's break down the 4 major barriers that are in the way. Starting with the large-scale production dilemma. The first and perhaps biggest obstacle is manufacturing high-quality graphene on an industrial scale. The method that won the Nobel Prize, mechanical exfoliation, is literally using adhesive tape to peel off layers of graphite and produce graphene of extremely high, almost perfect purity. The problem? It only produces tiny flakes that are insufficient for any macroscopic application. It's like trying to build a house using only one perfect grain of sand at a time. For industry, the most promising method is chemical vapor deposition. In this process, gases containing carbon, such as methane, are heated to high temperatures in a vacuum chamber with a catalytic metal sheet, usually copper. The methane breaks down and the carbon atoms deposit onto the copper, forming a graphene film. Sounds great, right? But this is where precision engineering comes in. This process can create defects. The graphene sheets grow from multiple points, creating grain boundaries, which are like seams in a fabric. These seams and other point defects, like missing atoms, drastically compromise the material's electrical and mechanical properties. For a processor, a single grain boundary in the wrong place can render the entire chip useless. Obtaining a sheet several meters long with single crystal quality and no defects is still a monumental and extremely expensive challenge. Then we have the challenge of integration and functionalization. Okay, let's say you manage to produce a perfect sheet of graphene. Now what? The second challenge is integrating it into an existing product. Graphene by itself is a 2D sheet. How do you turn it into a 3D wire, into a composite with a polymer, or deposit it onto a silicon wafer without damaging it? Transferring the graphene sheet from the copper substrate where it was created to the final substrate, such as the silicon of a chip, is a delicate process that can introduce wrinkles, tears, and contamination. Furthermore, its chemically inert nature, which makes it so stable, also makes it difficult to bond with other materials. To create a composite, for example, it's not enough to just mix graphene powder into melted plastic. The sheets tend to clump together due to van der Waals forces, forming graphite clusters instead of dispersing evenly. This not only cancels out the benefits of graphene, but can also worsen the properties of the original material. Functionalization, which is the chemical engineering process of adding functional groups to the surface of graphene so it can bond better with other materials, is an active area of research, but it adds complexity and cost to the process. And the cost-benefit analysis is also very important. Here we get to the most pragmatic point of engineering: money. High-quality graphene is extremely expensive to produce. For most applications, it doesn't compete with established materials, but rather with incremental improvements to those materials. Let's think about flexible screens. The material used nowadays is indium tin oxide. It's brittle, but it's transparent, conductive, and more importantly, the industry has decades of experience and infrastructure to produce it at low cost. Graphene is superior in flexibility, but the cost of production and integration is still very high. The industry wonders, is the consumer willing to pay 50% more for a phone that bends a little more without breaking the screen? In most cases, the answer is still no. Graphene needs to be not just better, but so superior that it justifies replacing an entire production chain and the significant increase in cost. For now, this window of opportunity only exists in very high-value niches. And of course, we have the lack of industrial standardization. What exactly is graphene? Is it a single layer of carbon? Is it less than 10 layers of carbon? And what is the acceptable percentage of defects? Today, there is no universal industrial standard. A company can buy graphene powder from a supplier and receive a material with 5 layers and few defects. On the other hand, they might receive a powder with 50 layers, which in practice is just ground graphite. Both are sold as graphene, but their properties are completely different. This lack of standardization creates huge uncertainty for product engineers. How can you design a component if the raw material doesn't have consistent properties? Without clear quality and metrology standards, mass adoption in critical sectors like aerospace, automotive, and consumer electronics becomes unfeasible. So is this the end of the graphene dream? Absolutely not. The graphene revolution hasn't been cancelled, it's just not being televised. Instead of a disruptive change, we're seeing a quiet evolution. Graphene is already here, but in applications where its unique properties justify the cost and challenges. It's in composites for tennis rackets and in bicycle frames, making them lighter and stronger. It's in tires, improving grip and durability. And it's also used in anti-corrosive coatings and heat-dissipating paints. In laboratories, it drives ultra-sensitive sensors and new research in electronics. The journey of a material from the laboratory to our pockets is long and full of engineering challenges. Graphene is not a miracle material that solves everything, but a powerful technological platform. Every day, engineers and scientists overcome a small part of these barriers, making the process cheaper, more reliable, and more scalable. The future of graphene won't be an explosion, but a gradual and steady infiltration into our technology. And if you've made it this far and enjoyed the video, take the opportunity to subscribe if you haven't already, leave a like and hit the notification bell. And you, which of these 4 barriers do you think is the most critical to overcome? Production, integration, cost, or standardization? Leave it in the comments because I want to know. On the side, there are 2 interesting videos you should watch to expand your knowledge and curiosity. If you want to support us, like, subscribe, turn on notifications, and consider becoming a member. Thanks, engineering enthusiasts. See you in the next video.